this, so I don't want to belabor this too much, but just to compare the atoms to material, and you know that in general, you can think of metals oftentimes as having like a range of energies, especially like near the ground. So basically there's not much energy, but then as you go to something and so there's essentially the impact cycle. And so that means that they're going to be kind of quasi-level systems in semiconductor type materials, so insulating materials. You can actually look at these interesting, first of all, on the left, is kind of like a quasi-atomic system in which you have individual atoms which are either layers or other ligands like lithium that actually have like a relatively narrow transition. So you can see here, for example, there's relatively narrow transition associated with exploding 3+ ion, so basically excited in alumina, possibly through electrical or optical doping, or excitation, sorry. And then this actually couples to this very narrow transition here. And then you can see similar things can happen in neodymium. So neodymium has like a well-known 1.06 neutron transition, and so that transition actually is kind of a cornerstone for creating the neodymium mag laser. So that's something that's used for green laser craters as well. But if you look at the neodymium glass, what's kind of surprising is that the transitions actually slightly different wavelength. So then the reason why is basically the dielectric environment slightly influences the energy of the transition between two otherwise identical states. And then if we look on the right, then you can actually see that the transition happens a little differently. Where basically, rather than having very discrete states that are associated with these rotor transitions, we instead have oftentimes, like for things like gallium arsenide, we have a range of conduction depth energies and energies. But we oftentimes have the laser transition happening near the band edge of the semiconductor, and that's like kind of a quasi-level system. However, the efficiency is not necessarily that great if you just do this at all, as I'll explore further. So there's actually a number of strategies where you basically try to tightly define the states and actually eliminate these extra states that can reduce the efficiency, such as quantum wells and the first quantum wires, quantum dots. And so all these quantum designs, right, so without going into too much detail, can give you like much sharper transitions than you would otherwise get. And so sometimes these are called artificial atoms even. Just an example of that is up here. And so this is a picture from a lab in Arizona State that's basically showing you that if you take these semiconductors and if you make them into quantum dots with well-specified radii, then they can actually have very strong transitions at targeted colors. And so you can basically transfer to almost any color in the rainbow very easily. And of course, this is actually a really interesting direction if you need an alternative to rotors for sharp laser transitions. And of course, in principle, this can be also much more efficient than having like a bunch of transitions like you have in the gallium arsenide laser. So any questions? Oh, here's something. Okay. So I have about 15 minutes. So now I'm going to try to introduce the general rate equations today. And then after I introduce the general rate equations, then we're going to try to use those to describe particularly like 3-level and 4-level laser systems. And then that will hopefully lead us back to understanding how do we use these kind of lasers for optical communication. Okay. So basically, the rate equations are critical because they're going to tell us, first of all, like what transitions are relevant in laser. Okay, so that's number one. And then number two is it'll tell us how much power we get out of the system and also how efficient the system is in the presence of other processes. Because there are many processes happening in these laser systems at the same time, so you have to look at all of them at once and capture at least like the most critical transitions in changing the population sometimes. Okay, so basically, the way that we'll try to construct the rate equation will start with the laser transition. And so here, it basically written as 2 and 1, where basically N2 is associated with the population in the state 2, and then N1 is associated with the population in state 1. And we're assuming that N2 minus N1 is supposed to be positive equivalent. Okay, so that's a population inversion. So these 1 and 2 states are basically the population inversion states. So of course, there can be many other states in the system. I can show you a whole bunch of examples that are more realistic, but this is like kind of a population inversion. So what else is happening here? So basically, you can see there's spontaneous emission process. So basically going from 2 to 1, and we said that that's inherent to all these systems. So we always have spontaneous emission. So we need to capture that, we calibrate that. But then there's also potentially non-linear transitions. And so you don't always have non-linear transitions going away, and we should have and then you can have like this cateching process where basically you go from excited state to some other state where we get less rock. So we need to know how this can happen. And then another thing that's really critical is that the 1 state can't be drained. So the 1 state is very important that the 1 state can be drained. Yeah, that is a helpful approach to playing this in noise. Right, exactly. So the point is, if you don't have any failure for the 1 state, then it's almost impossible to maintain population inversions. Pulled out, and then we have to be able to pump it back to state 2, right? So first, pull energy out of the ground state, quote-unquote ground state, in the laser transition, and then push it back to the state. So you have to kind of do both and maintain that cycle. Yes, exactly. So if you go back to some of the examples that we had earlier, just to kind of illustrate this a little more, you can see that actually the foremost excited state is actually the single appealing group, which is in the upper left up here. And so this is like something we're trying to get to. But then if we look at it in terms of the terminology we just defined, then this is basically our state 2 here, and then this is our state 1 here. You can see that this is not the highest excited state, and this is also not the lowest ground state, but it's actually, these are both intermediate states. And then there's like a low ground state that's all the way down here. It's actually off the chart. Right. Well, so I think the point is both are possible, but it also depends on the environment that you're in, right? So if you're in an environment where 633 nanometers is selectively enhanced by mirrors, like you basically designed it so that you have feedback, then you're going to preferentially emit 633 because the stimulated emission is pushing you in that direction because of the presence of 632 nanometer photons already. So if you have something that basically jams out the 3.39 micron, you won't have like phasing at that movement. But if you design it the other way, you wanted to encourage 3.39 microns, then you can do that. But one of the key points here is that these two transition wavelengths are like well separated from one another. So usually you can design a laser to have one or the other. So usually you don't want both in general. Usually you either think about bringing visible values like laser pointer, or you're doing some sort of infrared spectroscopy or something, so you need the 3.39 coordinates. So you kind of decide when you design the laser which one you encourage. Sure. Yeah, sure. Yeah. Well, the transition is happening in neon. So I think the way to look at it is helium is there to help us with the pumping because it's possible. Helium has much simpler set of states, so you can reliably get to this very high energy excited state of helium through voltage discharge into the gas. But then you need it to basically collide with the neon atom so that neon atom gets to this 2p5 by that state, and then basically has the laser transition. So that basically is happening. And then of course it loses the rest of its energy subsequently, typically through non-radiated collisions until it basically resets and then allows you to keep pumping the helium in the neon. Sure. Okay, so then going to the rate equation real quick. So basically the simplest way to look at the system is following. So if we say that there's isolated two-level system, the first is a simplification, then the rate at which the upper level energy or population changes would be dependent on three factors. Okay? First factor would be basically the spontaneous emission decay. Okay, so that's this minus nt over t spontaneous. The next term would actually be excitation from absorption of photons. Okay, so this is n bar, so that's the average number of photons interacting with it, times n1 over t spontaneous, so that's the absorption term. And then finally, we have basically the stimulated emission term, which is minus n bar nt over t spontaneous. And so then this actually shows you why you need to have, like in very concrete terms, why you need n2 greater than n1. Because otherwise, like, you'll have basically, as n bar becomes positive, then you actually otherwise have like excitation of this two-level system beyond what you want on the input byte. That's the opposite of what you're looking for. So that's an absorption process if n1 is greater than n2, but on the other hand, if it's n1 less than n2, on that, then you have stimulated emission. So that basically what this is showing, just in a simplified case. And so if we just write this down in slightly different terminology in terms of this delta n, then we can write down now the delta n differential equation. So that's just derived from the equation for NTU, assuming NT plus n1 is equal to some fixed order. Now we have basically that the delta n depends on the spontaneous emission by plus the population of photons. So basically these two terms add together minus this so-called NT, where NT is basically the total divided by T spontaneous. So that last term will always be negative, but then the first term should also be negative if we write it this way. And so that gives us like a very simple solution. So if we just solve the differential equation, I won't go through the math, but you know how to solve this sort of differential equation. So basically you got like an exponential, where basically it's a constant times this e to the minus 1 plus 2 n over pi spontaneous times the time that's flat minus the constant. Okay. And so if we look at like what that means in the absence of pumping, that just means that you'll have exponential decay of photons, right? And so that's because like you have absorption process. So just to show you completely what happens, if the light is off in the system, then you see basically the amount of downstate energy basically goes to 1 over time, right? Which is expected. So that basically just reverting to thermal equilibrium. However, if you turn the light on, then of course you go from thermal equilibrium state where basically almost all the population is in the down state to something where you have much less energy in the down state, right? And you have much more in the inside state. So then basically your delta n is going from minus 1 to something that's close to 0. However, the key thing here is that it's not going exactly to 0 or positive value. So that's telling you that even if you're putting a bunch of optical light into the system at the transition rate, you can't really push it into population inversion. And of course you can like turn the light on and off and on that will go into inversion. It's just never going to go into inversion. That's basically determined just by the structure of these equations. But it can't go into inversion just from the pumping of basically the two-level system. So that tells us like two-level system by itself without any external interaction will never be laser. So you have to add something that's kind of about it. So we need a process that will both increase the number of atoms in Q while also decreasing the number of one, which kind of body equality product. So we need to look at the three-level, four-level systems that can help us achieve that. So just as an example, basically we have a very simple concept here where we just have some pumping rate of RT. And so now RT is basically just adding positive term into our EM to T differential equation. And otherwise, like, it's very similar. That's great. And then the second thing we have is a minus R1. And basically R1 is basically pulling energy or population out of this lower state. Okay, and this could be non-linear process, it could be linear, possible, it's just so the key thing here is that now we have this positive R2, and we have this R1, which is defined with minus sign, so basically negative for 1. And so basically doing both things at the assumptions about O1 and O2. And so this tells us that if you look at this expression, like the form of this, then you can see that basically positive R2, as we defined it, will increase like the reactive population inversion that's possible in steady state, as well as like a positive value R1. And of course, with that said, that does put certain constraints on the ratio between tau1, like basically the spontaneous decay of like this ground state and transition, divided by the spontaneous transition between two. And so you need actually in general, if you want n naught to be positive, you need tau1 to be less than this spontaneous transition between two. So basically, in the ideal case, we have like a relatively large tau2 or tau1, and we also have like a relatively short R1. But in general, R1 and R2 large is most likely. And this is basically just showing that typically we can assume that the tau2-1 is close to the spontaneous emission lifetime, so that can help us understand like conceptually what's happening. And of course, tau1 should be less than the spontaneous emission lifetime in order for this population inversion to be large. So then basically, like just to expand on those previous equations, like basically it was slightly simplified because we didn't include all the transitions that take place. We basically just included the first two terms, but we also need to include both stimulated emission and then absorption. Okay, so if we add stimulated emission and absorption both, then you see they enter both of these differential equations with the upper and lower state, but they have opposite signs, so basically it takes away from like the stimulated emission takes away from population of N2, adds to N1, and then of course absorption of incoming photons adds to the population N2, subtracts from N1. So you can see in both cases, like basically we're adding terms that are dependent on this population difference, N2 minus N1. And so in order for the population inversion to be maintained, then we have to have a pumping rate that overcomes the drain that's associated with operating the laser system. Right? And so hopefully that makes sense conceptually, that to maintain the steady state, we can't basically be pulling more energy out from stimulated emission than we're adding back into the system, while including like parasitic processes in the system. And so the way we can illustrate that general framework is that we have this pumping rate RT going into this upper level system of T, and then we basically have this spontaneous lifetime, okay, and that's causing some decay, and then we have stimulated emission as well, causing additional decay, and then we have some absorption. That absorption partially offsets the stimulated emission, but the net effect is basically some stimulated emission is happening, and then that stimulated emission needs to not be happening faster than R2. Like ideally, R2 is equal to the stimulated emission plus spontaneous emission plus any other loss mechanisms. So then you can maintain like a steady state population inversion between these two systems. And so then if we solve this in the steady state, then we basically get the total population inversion is going to be this n naught that we calculated earlier, divided by a factor that's 1 plus tau spontaneous times the transition rate, which again is close to the inverse of the spontaneous emission lifetime. And so you can see this tau s is basically going back to the previous picture, dependent on tau2. So this is basically the total rate of loss of the upper level state 2 plus some additional contribution from tau1, the loss of the lower level state times the convection factor. So I think that pretty much gives you an idea. It's just showing what the steady state population difference looks like as a function of W5. So first when WI equals 0, then we get the previous result that we calculated earlier, but then it basically starts dropping pretty substantially as we go to larger values. Online simulation and more for nanotechnology. Okay, so welcome back. Today's lecture is going to be on wavefront division multiplexing, and we're going to divide it into three components. The first will be the fundamental principles of wavefront division multiplexing, and then second would be kind of the key hardware components that are necessary to create the WDM network. And then finally, we'll talk about how optical networks using WDM are kind of merged in together with basically all the other networking that we know, such as packet-based networking and Ethernet. So the first topic, just a brief recap, and it's going to be very short. Remember in the first week we talked about that there are different types of multiplexing schemes, and that there are actually at least 3 different types that we identified. The one that we'll be mainly focused on today is called essentially frequency division multiplexing or wavelength division multiplexing. And in this first case, basically you choose a set of distinct frequencies and then you send separate signals down each one of them. The other two approaches, basically time division multiplexing, the idea is that you have a time window for each different signal, and so you can have up to n signals within each time window, and then you get a new time window every so often, and that's basically illustrated on the right. And then the third approach is basically co-division multiplexing, so that's somewhat analogous to TDM, but instead of just having a signal in a short time period, it's kind of spread out over some longer time period, and they're interleaved in various ways. And we talked about that previously. However, today we're just going to focus on the first type of frequency or wavelength division multiplexing. Okay? So basically WDM and FDM are the same thing, just to be clear, but WDM is probably more common acronym nowadays. And so you basically need to know what kind of wavelengths you can deal with. Okay? And so this is just showing kind of the whole low loss range in the spectrum of dry optical fiber. So it actually extends from about 1260 nanometers all the way past 1600 nanometers. So each of these bands can contribute something to frequency division multiplexing. This is just showing kind of an old example where when you have 100 gigahertz spacing between each channel, and then you use the C or conventional band, then you can fit up to 40 channels within that range roughly. And so, of course, if you extend it to include other ranges outside of conventional, such as short, long, and ultra long, or even go back to the original set of wavelengths, which is centered around 1300 nanometers, or an extended range that's between the two, then you can actually encompass many more channels, okay, than just 40. the total bandwidth is really just the sum of the contribution of each of these individual channels. Typically, each channel would be basically fairly similar to the other channels in the communication wavelengths, and oftentimes there's also some kind of control bandwidth, but we're not going to focus on that today. But then the total bandwidth is just a sum of the contributions from each wavelength, right, which hopefully makes sense. And then, of course, the total number of channels available will depend strongly on the spacing. So obviously, the wider the spacing, the less number of channels you can fit into a given wavelength range. And then another key measure of performance is called the spectral efficiency. So that's basically where you take the bandwidth or bit rate of each channel, and then you divide by the frequency spacing. Okay, so of course you want this to be maximum for best performance. When the book was written around 2000 or so, originally, this value was actually pretty low, oftentimes around 10%, but of course more recent systems are getting much higher, closer to about 80% plus. And that's before you use any other tricks in order to improve the performance further. So basically, the reason why this is not trivial to get high spectral efficiency is because of crosstalk. So in other words, if you have channel A and channel B that are closely spaced, if any signals from A feed into B because it's too wide wavelength, then that's going to create a substantial amount of crosstalk, basically always unhappily otherwise desired signal. And so traditionally, basically the approach was to see that channel spacing should be steadily lower than these channels. So basically that's where this delta is. So this implied typically for bandwidth, bit rate was like on the order of 50 gigabits per second or so, then you need channel spacing of at least 100 gigabits. However, nowadays, I don't think anybody's really using that. I think there was a move relatively early on, kind of over a decade ago, to move to dense wavelength version multiplexing by having this channel length to 15 gigabits. And then it was halved again to 25 gigabits, and this is still called DWDM. But now there's also this ultra dense wavelength division multiplexing, UDWDM, that's at 12.5 gigabits basically. And so you can actually start squeezing these very close to each other. And of course, this is intended to improve performance. So let's give you a rough idea of how this works practically. The total wavelength range for DWDM is typically starting from this C or conventional band, which goes about 1525, 1565 nanometers. The reason why this is so important is because that's where EDFA has the best amplification, but you can also go to long wavelength band, 1570 to 1610 nanometers, which is a faster band, and you can also have a reasonably high gain in the image as well. So you can actually use both of these channels. But if you are able to take advantage of the bands further, because we have the capability besides just kind of standard EDFA, then you can also start including double band, as well as like other ranges in between, and then you can potentially get this whole range about 1260 to 1610 or even 1. And so you can have anywhere basically a total range of frequencies that goes from about 5 terahertz up to 50 terahertz or slightly more. And so then if you look at this table, this is just showing the number of channels based on the channel spacing chosen. So it's a kind of a traditional WDM numbers. You can see that you have about 20 channels in each of these lower bands, but then you can get 800 or that whole range of low losses. And then these are doubles as well to dense wavelength vision multiplexing, and doubles again for ultra dense. Right? And so in the kind of best case scenario of ultra dense across the whole band, you have about 100 channels, which is a good of these channels. So basically now I'm going to talk about the hardware that goes into the DWDM. Okay. So there's actually a whole lot of components that you need in order to make a very intense wavelength vision system. Okay, and so here I've just listed all the components that are needed. So it sounds like a lot, obviously. But the good thing is that a lot of these components have been developed digitally. So it's not like you really need to understand like tuning different multiple concepts. But basically a lot of this is driven by filters. Right? And the reason it's very simple because like since it's wavelength division multiplexing, you need to have wavelength selectivity. If you don't have wavelength selectivity, you can't really do much of this stuff. If you do have it, then that enables most of these items. There are a few items that are not wavelength selective, such as star colors, but everything else is usually wavelength selective. So what do you need in a filter, since that's a really important component? Of course, there are a lot of things that you want in tunable optical filter. So of course, tuning is the first thing, and that's actually by itself not trivial. But then you also need low crosstalk, so that means basically it's highly selective. So you're tuning at too low wavelength, but it's not reflecting other wavelengths. And then you also want it to be fast. You want it to be low loss, so in other words, not basically cause you to have to amplify it again. You want it to be stable with respect to the environment. So in other words, if it gets hot or cold or humid or dry, then you don't want it to screw up, basically. And of course, on top of all that, you want it to be cheap. So that's a lot to ask, obviously. But there are a few potential solutions. Because this time is limited, I'm just going to kind of briefly touch on some of these, but of course I can answer any questions later. So basically there are 4 major types that are well known. And so the first is essentially fabric growth cavity. Fabric growth cavity, the concept is very simple, which is you have 2 reflectors, and then you tune the spacing between those 2 reflectors. And then that actually tunes the resonant wavelengths in the system. And you can actually tune like a large number of channels if it's a large enough cavity. But of course, you also need to be able to the cavity precisely enough so you can select the wavelength you want in the right bandwidth. So you need very good mechanical control there. Of course, this disadvantage potentially is that high precision can be more expensive, and then the second disadvantage is if it's a large mechanical object, it can take a while to move. So then oftentimes you want to use like micromechanical surveillance devices, so it's fast enough to keep up with everything else. Okay, so that's one strategy. The second strategy that's actually much faster potentially is the Mach-Zehnder interferometer. And so Mach-Zehnder, of course, is basically just analogous to Nicholson interferometer or the other interferometers that people learn about in undergraduate optics and so on. So basically, it's just like you have 2 arms, and then the phase shift between those arms. And that's captured as basically a time tap. And so basically the concept is just that your frequency times L, and the delay is basically setting a phase shift, and then that's creating like a transmission spectrum, or basically a series of peaks of certain wavelengths that are being highly transmitted. And so then that means that you can like send basically broadband wavelengths, but then it only